Okay, I'm going to be looking at the introduction to complex and imaginary numbers. So why do we look at complex numbers? Well, if we look at the quadratic formula, we always knew at GCSE if our discriminant was less than 0, we would have no real roots. So if we would have a quadratic and it was less than 0, we would have a quadratic that would give us no roots. And if it equaled 0, for example, we would have 1 root if we touch it, like so. And if it was greater than 0, we would have, in this case, 2 roots. So that's a look back at GCSE. So in that case there. But in the case here, if it's less than 0, we have no roots. Now, in complex numbers, we can look at introducing I equals the square root of -1. And this helps in many ways looking at dealing with complex numbers. So -1, the square root of -1 is an imaginary number and it's in the form bi, where b can be an element of any real number, for example I, 3i, -2i, I pi, and so on. And a complex number is in the form of a plus bi, where a and b are elements of any real numbers. So 1 plus i, 3 minus 2i, and so on. We say a is the real part and b is the imaginary part. And we've got a lot of varieties of where this comes in handy, but I'm still in my early days of learning this content, so I will cover that in a later video. Other practical applications, it comes up in factorials. A Mandelbrot set is the most popular factorial. We'll see how this works later. Analytical number theory. So number theory is the study of integers. Analytical number theory treats integers as real/complex numbers to use other analytical methods to study them. For example, the Riemann zeta function allows complex numbers as inputs and is closely related to the distribution of prime numbers. And it's used in physics and engineering, so signal analysis, quantum mechanics, fluid dynamic, relativity, and control theory. But again, lots of things above my pay scale. So let's have a quick look at it. So remember with third law, all the way back at GCSE, third law states square root of a number. So root 3 times root 12 equals root 36, 3 times 12. That gets us 6. Or we could say plus or minus. Now, in terms of negative roots, so we had negative root 36. That would equal -1 multiplied by root 36. And we can have that as 6i for this example here. If we look at the other one, so for example, we had the square root of -4, that would become root 4 times root -1, and you get 2i. And lastly, root of -7 would be root 7 times root -1, and you would get that as root 7i, for example there. So nothing too worrying, but make sure you don't confuse it. So a misconception could be if you wrote the square root of 7i, that's naturally incorrect. So just make sure you have very clear handwriting when writing that. Okay, if we look at the double bracket option in terms of adding and multiplying, the first one, it would be 2 plus 4, that gets us 6. And 3i plus I, collecting like terms, you get 4i. In terms of, again, this is sort of your standard brackets, I minus 6, and then it's -3 times -i, so you're going to get plus 3i. So you're left with I plus 3i gets us 4i, and we're left with -6 there. And lastly, same concept with the bracket, with the division, I should say. Everything's divided by 2, so you get 5 plus 2i. So nothing new there. So this helps us with solving quadratic equations. So just as we tend to use x as the default real numbered variable and n for integers, when we use complex numbers, we tend to use z as the default letter for complex numbers. So here, z squared plus 25 equals 0. Naturally, at GCSE, we would have no solution, but at further maths A levels, z squared equals negative 25. So when we square root both sides, we get the square root of negative 25. So that is root 25 multiplied by negative 1, root to negative 1, and you get plus or minus 5i. Lovely. Here we got a quadratic, z squared plus 3z plus 5. Naturally, if I flip over to decimals, and if I was to type that in, well, I'll do x squared for this case, x squared plus 3x plus 5. We can see here, it's very close, but you know, there will be no roots, essentially, or no real roots. But if we look at it in terms of complex numbers, we come back to the equation. We can use our quadratic formula in this case, or we could complete the square. Quadratic formula would be z equals minus b plus or minus b squared minus 4ac all over 2a. So z equals, well, b would be 3, so minus 3 plus or minus b squared would be 9 minus 4 times 1 times 5, so minus 20 all over 2a, so 2 times 1, 2. So instead we equal minus 3 plus or minus, so we're going to do 9 minus 20, which is negative 11 all over 2. So this is where it would break down, if you will. So z equals minus 3. So that negative 11 become root 11 times root minus 1. So we'll get plus or minus root 11 I all over 2. Or we can rewrite that as minus 3 over 2 plus or minus root 11 over 2 I. And there you are. And those would be our two roots. Fantastic. Okay, that's the introduction. So this is where you would, I'm following the Edexcel book, so you can have a go and look at the questions for Pearson Core Pure Mathematics Book 1. And I've taken the last question from exercise 1A and 1B, and I'll have a look at that now. So given that z equals a plus bi, and w equals a minus bi, where a and b are elements of real numbers, show that z plus w is always real. Okay, z plus w. So that equals a plus bi plus a minus bi, and that equals 2a. Therefore, always real, because the bi and negative bi cancel each other out. So that z take away w is always imaginary. A plus bi, take away a minus bi. So you're left with a plus bi, take away a plus bi, and that equals 2bi. Therefore, always imaginary. And there we are. Okay, question 6. This is the last question on exercise 1B. So we want to show that the equation z squared plus bz plus 11 equals 0, where b is an element of real numbers, has distinct non-real complex roots. Find the range of possible values. So for non-real complex root, our discriminant has to be less than 0. Okay, so b squared minus 4ac has to be less than 0. So when we look at this, b squared minus 4 times 1 times 11 minus 44 has to be less than 0. So therefore, b squared minus 44 has to be less than 0. B squared has to be less than 44. So when we square root this, b has to be less than plus or minus root 44. So naturally, for example, negative root 50, if I squared that, that would be larger than the negative 44 squared. So when we do an inequality here, b has to be less than positive root 44, and it has to be larger than, in this case, negative root 44. Because if it was larger than it, it would be, for example, negative root 9. Negative root 9, for example, squared would get me 9. And then naturally, let's check it out now. 9 minus 44, yes, less than 0. So we can keep it in that form. Or we can say b is less than 2 root 11 or larger than negative 2 root 11. Both would be acceptable. And we are good there for our possible ranges of b. And that ends the video.